Alright, hello and welcome to week 4. We are going to talk about sets for this set of slides. See what I did there? But first, because this is week 4, remember that in week 6 we have a midterm, okay? Dun dun dun. Week 6. So, let me talk to you about that, and then we'll go to sets. So, I will eventually make this midterm 1 module available on Canvas, and there will be several things in it. The things that I will be giving you right now are these 2 pages, midterm 1 info, and then extra credit assignment make midterm 1 review materials. Okay, so let us go to both of those and see what they're all about. So let's talk about the midterm. It will be on Canvas it'll be available between 2:30 on February 18th and 5:30 February 19th. That is a Thursday and a Friday. Dun dun dun, 18th and 19th is a Thursday and a Friday. And you can start whenever you want within that time window, okay? But once you click start, you're going to have an hour and 15 minutes to take the exam, okay? So just remember that, keep that in mind, unless you have DSPNS accommodations, then you'll have longer time, of course. So just make sure to start by like 4:15 p.m. on the 19th if you're going to wait until the very end of the range, okay? Because if you start any later than this, you don't get the full time, yeah? So, there won't be a lab that week because it will take place, we'll say, during lab. So it'll be 2 lectures and then you'll take the midterm. All right, so that's the idea. And then the midterm will be on the topics from the chapters and things that were due up until and through week 5. Okay, so unfortunately, homework 3 is not really due. Or sorry, homework 2 is not really due until week 6. So I'm not going to really touch on sets, the topic that I'm about to teach you on the midterm. So it's really just going to be chapters 1 and 2, maybe a little bit of the sets stuff I will throw in, but maybe not, okay? It's most likely just going to be logic and proofs, all right? So, and then you'll just study homework 0 and 1, as well as read your book to prepare for that. And because I cannot possibly ask you to write down esoteric, like, symbols for and or and implication and things like that on a test, I'm going to make the midterm entirely multiple choice. Okay, so that's how it's going to be. That might be the usual thing for this class. As well as the proofs chapter, oh man, I can't. It would be cruel and unusual to ask you to write a proof in an hour and 15 minutes under a deadline. That would be the worst thing in the world. So you're welcome. It's going to be multiple choice, and that's that. And finally, the test is going to be open book and open notes, because I'm not going to like force you to get Proctorio or something like that. That sounds horrible. The one thing you can't do is talk to another human, so don't like open up your chat application and like talk to people on Discord about the answers. Please don't do that. Otherwise you will face my wrath. So that's it. That's your midterm. Hopefully it's not going to be the end of the world. And yeah, just let me know if you have any questions. And let's move on now to the extra credit assignment. So this hopefully helps you for the midterm. So this is going to be an extra credit assignment worth up to 2.5% extra credit. So that's just added on to your final grade. So for example, if your final grade was 88%, then if you did the full credit for this, it would bump you up to a 90.5. Yeah. So yeah, just read everything, make sure that you understand all this stuff in order to get credit, and no late submissions are allowed for this. This is extra credit, of course, and so I'm going to be very, very tough on the deadline. Okay, it's going to be due February 17th at midnight. Okay, that's right before the exam gets released. All right, so that is that, and you have 2 options. You can do option 1 or option 2 for the extra credit, and I encourage you to read all this. But in essence, you're going to make some kind of review for the midterm. So make up some questions maybe and some answers and walk through them. If you record a video, you can use like Zoom, or I use OBS to do my video recording. Let me know if you have any questions about that. If you want 2.5% extra credit, make a 20-minute video. You don't have to edit it or anything, but it should be that length. And if you want just 1.25% extra credit, you can make a 10-minute video. Okay, so yeah, just make sure to follow all these guidelines. You got to make up examples of these concepts that will appear on the exam, and yeah, just explain everything that you're doing as you make your video. Option 2 is if you don't feel like recording yourself, you can make a write-up. So you'll do some typing, and again, you'll make up some examples, and you'll explain stuff. And yeah, that'll be that. So you're essentially writing the review in that case. And so if you want 1.25% extra credit, make a 250-word write-up. 2.5 will be a 500-word write-up. Okay, and this includes code. If you choose to write any code, you can just copy and paste that in and let Microsoft Word count those words still. Okay, so that is that. So feel free to include some code if you think that would be helpful for your review. Yeah, hopefully that all makes sense. Yell at me if it doesn't, but that is the midterm and the extra credit opportunity. Please take advantage of that. All right, so now it's time for sets. So here's all the stuff that I'm going to be teaching you, that I'm required to teach you, and let us motivate this. So sets were invented by this wonderful, wonderful man. He's German, and his name is Georg Cantor, I think, is how you would pronounce that. And the goal of sets, the set theory stuff I'm about to teach you, is that we would like to define all of mathematics with them, with some kind of common language that we can all talk to each other about and understand, okay? And this is a wonderful, wonderful tool for that. All right, and so this actually came to fruition. This happened. We have defined all of mathematics with set theory. And if you take any more advanced math classes, you'll probably see what I mean. All right, and actually, if you've taken calculus, you will probably have seen some of the stuff that I'm about to teach you, but maybe you didn't go over it in class. It was just in the book, and you didn't know what those symbols meant. So now you're ready. Okay, so let's get into this. Let's talk about what a set is. So a set, as far as definitions go, is not a very complicated thing. It's just a collection of objects. So it's like you got a box, and you put some stuff in the box, and the stuff inside is your set. Okay. So those objects, they really can be anything. If you would like to mathematically formalize the set of all green M&Ms in the universe, that's totally fine. And that is still math, okay? So sets are really not too bad. It's a bit of a breath of fresh air after proofs, probably. So yeah, the objects in a set, so you're putting a bunch of stuff together, a bunch of objects together. Those objects are called elements, okay? And that's the technical term that we use. And normally, we like to describe a set, if we can, if it's finite, by listing all the elements that are in that set. So, for example, we can define the set A to be the set containing 1, 2, and 3 as its objects. Okay, so you always put these braces. These delimit the set. So you put stuff in here. So like this is your set C. So all of C's objects are in here, separated by commas, okay? C's objects here, okay? So yeah, just remember those. This is called roster notation. It's like you're reading off the attendance in a class, and you're listing all the things, all the students in it, all the elements in your set. Okay, so here are two sets. A is the set containing 1, 2, and 3. B is the set containing 2, 4, 6, and 8. And the one key thing that might trip you up is that sets don't care about duplication. So repeating elements doesn't actually change the set. So for example, the set 1, 2, 2, 2 is just the same as the set 1 and 2. We don't care about duplicates. We get rid of them, in fact. So these are the same set, even though we usually write it like this. Okay, so just keep that in mind. Duplicate elements do not count. Okay, so we get rid of those. So that is it. That is sets. And obviously, we're talking about math stuff, so there's a ton of notation to go along with them. And I'm very, very sorry. This lecture is going to be mostly notation. And that is very unfortunate, I know. But we just have a lot to learn about how we talk about sets. And then we can actually do useful stuff with them later in this chapter and then in future chapters. So this is like building up all of our tools. So with that in mind, just remember that I'm going to have a lot of bold things today, and I'm sorry. Okay, so the elements of A are like the stuff that's inside. So each object is called an element, right? So we say that 1 is an element of A because it's right sitting in there, inside of the set A. And we like to write this using Greek for no good reason. This is like an epsilon, right? And so E stands for element of. But I will probably pronounce it as in. It's a lot easier and quicker. So 1 is in A, because yeah, it's sitting right there. Totally. Similarly, 2 is in A, 3 is in A. But 4 is not there, because this is A. It's like 1, 2, and 3. 4 ain't there. No, it's not inside. Not inside of A. Yes? So that's that. And then, of course, if you can have things, you can also not have things. So there's a concept of an empty set, which hopefully all this notation does eventually make sense. It should be kind of intuitive. Sets are not too bad, I think. You can write the empty set as just some braces next to each other, but usually we pick our own little special symbol for that, and it's this little O with a slash through it. Okay, so that's an empty set. You can have nothing there. It's like, okay, here's my set B. It's got nothing. It's the empty set. B equals the empty set. Likewise, you can have sets with stuff in them, and there's two kinds. There's a finite set and an infinite set. So a finite set is just one that you can list its elements, 1 through n. Like you can pick an n, like there are n elements in this set. And you can eventually count them if you had enough time. Infinite sets, of course, you can never count. Okay, they're finite. You would die before you could ever possibly get to the end because there is no end. Okay, so you can list out all the elements eventually if you had enough time with a finite set. Infinite sets are just huge and giant and never stop. For example, the set of all the integers that are positive is 1, 2, 3, 4, on and on and on, forever and ever. Yeah, so that's an infinite set. And when we do have finite sets, though, we like to talk about how big they are. And we like to use absolute value notation for that. So, for example, this is the set A. It has 3 things in it, so we say that its cardinality is 3. The size of A is 3. Yeah? So that's that. Now, we like to talk about all the integers, all the positive integers, a whole lot. And so we've come up with special symbols for those. So we have our n's and z's that I'm going to teach you right now. So n stands for the natural numbers, and z stands for the integers, and they're written like this. If you write them with your hand, this is how you do it. You put little 2 dashes there when you write your n. I'll do it again. 2 dashes, and then you finish the n. Okay, this is called the set of all natural numbers, and it's all the integers that are greater than or equal to 0. Okay, so it's this set, 0, 1, 2, on and on, getting bigger forever. Okay, it's an infinite set. And if you're a mathematician, you might see in a book one day that the natural numbers start with 1, but any mathematician who says that is just horribly, horribly wrong. So we just reject this idea. All of the natural numbers for computer scientists in CSCI are as they should be, starting with 0. Okay? So that's the natural numbers. And you may be wondering about this font. So this is called Blackboard Bold. And in your book, they're going to write n in bold, but no professor ever wanted to do this to try and drive the point home that, oh yes, this is the set n, because that took me way too long to write. This is much faster. That's why we do that. So that's n, and z is the set of all the integers. It's like, okay, we start with n, and we can build z from it because we just add all the negative stuff. So z is the set, 0, 1, 2, on and on that way, but also -1, -2, on and on that way to negative infinity. And you might be wondering why it's called z. It comes from the German word Zahlen, which just means numbers. Okay, so that's that. And z plus with that little superscript of a plus means the set of all positive integers. So plus for positive. So that's 1, starting with 1, 2, 3, getting bigger and bigger and bigger towards positive infinity. Okay, so that is n and z. You're kind of like building z from n. You can kind of go that way, which is fun to think about. Maybe I'll keep that for posterity. We can go even further. We can extend z to have even more numbers inside of it, more numbers that we like to use. How about the rationals? So q stands for the rational numbers, and r stands for the real numbers. So the idea with q is it's the set of all the quotients that you could ever make. It's the set of all a over b, where a and b are integers, and b is not 0, of course, because we can never divide by 0. So all the stuff that you could put in fraction form. And that includes all the integers, of course. Z's in there, because you can put just like 1 over 1, 2 over 1, -3 over 1. Those are all there. But extra stuff is there too, like 1/2 is now representable. 5.23, that's representable because you could put like 523 over 100. -5/3, that's there. It's all there. Okay, so those are the quotients. Those are the rational numbers. Now we could go this way again. We can extend the rationals. If you ever take an analysis class, you will learn how to do this. You can create the real numbers from the rational numbers by filling in some gaps. Okay, so the real numbers is essentially all the rational numbers plus the irrationals too. Okay, so we can solve all the polynomials, or at least more. And so it's everything from Q, but you also have these irrational numbers now. And there's a lot more irrational numbers than rational numbers, apparently. Pi, square root of 2, e, all the multiples of them, on and on and on until the end of time. So R is kind of the biggest set that we're going to consider in this class. So your book is always going to use bold because it's supposed to be bold, but I'm going to write N, Z, Q, and R, like that. That's how you write them. That's Blackboard bold for you. Okay, so this is where I just keep on piling on this notation, and I'm sorry, it's just going to have to happen for this lecture. It's really nice sometimes to describe a set in terms of another one. Like, okay, start with all the elements in S, and then just pick out the ones for that, such that this predicate P is true for them. Okay, so this is called set builder notation when you do this kind of thing. So you read it like this: A is a set of all x's in S such that P of x is true. Okay, you might see the colon in your book, but I also like the pipe. So these are all the same, interchangeable, no difference. So this is defining the set B to be, okay, all the x's in Z such that x is even. So take a second to think about what that might mean, and then here it is. So B is this set right here. It's, okay, take all the x's in Z and pick out the even ones. So 0, 2, 4, -2, -4, on and on forever and ever. So it's that set. It's a bit smaller, but we can start with Z so we don't have to define it in a weirder way. Okay, this is very convenient for us, you will find. And then this is a bit of a weird thing. It's called the universal set, and it will make sense, but it only makes sense in context. So if we're talking about something like, okay, I define a bunch of sets starting from the integer, starting from Z, maybe making them a bit smaller by picking out certain ones. The universe, like sometimes called the universe of discourse, then that's Z itself. Okay, if I'm talking about a bunch of different kinds of sets built from the rational numbers, then the universe is Q, and so on and so forth for different sets. So it's only ever going to make sense in some kind of context, and then it should be obvious at that point what the universe is. Okay, so don't worry about that for now. That will be useful later. And now finally, this is not a definition because you actually already know it, right? The Venn diagrams are something you already know and love. So I've drawn one before, so here's A, that's 1, 2, 3. We can draw it like this, a nice amorphous blob to represent the set A. And then B can be its own little amorphous blob that contains 1, 2, 3, and 4, but oh man, it shares some things with A. And this helps us discover what's in common. And this is kind of like the key of sets. When they share things, that might be important. Okay? The stuff that's inside defines a set. And so we want to be able to talk about what's inside, what they share, what's different, things like that. And Venn diagrams are one way of helping us do that. Okay. When you're making smaller sets from your set builder notation, or you're talking about stuff that's in common, you have smaller sets that you're making from another starting set. Okay? And so you have this kind of idea. So here is the set A, here's the set B. Let me draw them as Venn diagrams again. A is 1, 2, and 3, and B is 1, 2, 3, 4, and 5. So here's A, and B is this. So you see how B is bigger than A? A is contained in B. So that's what we mean by subset. So we say that A is a subset of B. And if you want to get all mathy, it's, okay, for all x, if x is in A, then it's in B. That's what it's saying. So yeah, if x is in A, then it must have been in B. If that's all true, then A is a subset of B. All right? It's just saying that every element of A is also an element of B. That's all it's saying. Notice, though, that just the way implication works, this also works when A is equal to B and A is equal to the empty set. Because, dun dun dun, A is equal to the empty set, well, yeah, I can just take nothing out of B, and that's still a proper, a nice little subset. It's not a proper subset. Well, it is a proper subset, sorry. I'm getting my words confused. I shouldn't have said the word proper, and I apologize. So yes, the empty set is totally, like, here's my C. C is the empty set. Yeah, it's totally contained in B because, yeah, there's nothing there. I can just choose to take no elements. Yes? So that's possible. And then A is equal to B is also possible. So if I picked, like, the set C to be all of B, well, yeah, every element's also in B, so it's a subset still. So it's kind of like, if you think about sizes, it's kind of like less than or equal to. And it kind of looks like that as well. It's like you just kind of made it round instead of pointy. So we write subsets like this. A is a subset of B. It's very similar to less than or equal to. And you can think of it in terms of sizes. Like, yeah, A contains all the elements that B contains, maybe a few less. But it can contain all of B because of that equality part. So that is a subset. Then you can have proper subsets, which gets a bit fancier. You just now have a side condition that you must be strictly smaller than. A cannot be equal to B now. So you write that as a proper subset B, which is essentially the same as less than B, because you can't have the equality there. You disallow that. Okay, so that's subset and proper subset. Let's have our examples now. So I've already shown you this. A is a subset of B, because all the elements in A, yeah, they're sitting there in B. Similarly, A is a subset of C, because all the elements in A, yeah, they're sitting in C. The empty set is a subset of any set, because you can take, you can just take none of that set. It's like, yeah, okay, I'll just take the none right there. Totally fine. And then for proper subsets, A is a proper subset of B because, yes, all the stuff is contained, and also B is bigger. Okay? It's not, we're missing that equality, so B has to be bigger in the sense of cardinality. Okay, so that's why we're defining all this stuff, so that this eventually makes sense. The empty set is, which is of size 0, is a proper subset of B because I can just take nothing, and yeah, I can find some nothing easily in any set. And it's strictly smaller than B because B is not itself the empty set. Likewise, we can put slashes through things. A is not a proper subset of C. So, because, yes, all the elements are there, but A is not strictly smaller than C. And this is just like we're putting slashes through this over here. We can say that 4 is not in A with the not in sign. Whee. And maybe I should have written that, sorry. Bam. So that is subsets and proper subsets. The exact opposite is a superset, and this should make a whole lot of sense now that we understand subsets. So we say that A is a superset of B, written like this, if you just flop them. B is a subset of A. Okay, so A is a superset of B if and only if B is a, I can just point to that, I guess. If and only if B is a subset of A. So it's just like you're flopping it. It's greater than or equal to now instead of less than or equal to. It's not a big deal. So, for example, C is a superset of A because, yes, C holds more things or the same amount of things as an A, and A contains all of C. Yes? So you can just think about that definition backwards. And likewise, B is a superset of C, let's say. Because here's all the stuff in C. Yeah, it's all in B, and also B is bigger. So you just think of it that way. And in fact, B is a proper superset of A, and it's a proper superset of C. Okay, they're the same set, so why not? Because, again, all the stuff is there, and also B is bigger. Yeah, it's like a greater than sign now. So hopefully this is all making some sense. I know it's just weird notation, but now we're ready to practice finally. So let's get some practice in. So take a second to pause the video. Here are my two sets that I'm defining to you. Figure out the answers to all these questions. Okay, so I'll give you some time to do that. And now, assuming you're back, let's go through your answers. Let's see what you thought. So the first question, A, is 1 an element of the set A? So the set A is 1, 2, 3. Yeah, 1's right there. Yes. Yes, it is. Similarly, is 5 in A? No, there is just 1, 2, and 3 in A. I don't see a 5, so the answer is no. And we could be explicit and say 5 is not, with a little slash through it like that. 5 is not in A. That's prettier. 5 is not in A. All right. 42, 84, that set, is that a subset of B? Okay. So what we need to do now is show that 42 is in B. 84 is also in B. Yes? Let's do that. So what really is B? B is all the integers that are themselves integer multiples of 42. So that is 0, 42, because that's 1 times 42, 84, because that's 2 times 42, negative 42, because that's negative 1 times 42, and on and on and on. I think you can see the pattern now. So it's just 42 times x. It's that set for all where x is in the integers. Written another way, yeah? And I think you can see, yeah, 42 is right there, 84 is right there. It's totally a subset. Yes. Is 1, 2, 3 a proper subset of A? And remember, this is like the strictly less than sign. And the answer is no, again, because no is equal to. It has the same number of elements, so it's not a proper subset because it's equal to. Okay, so the answer is no. But 1, 2, 3 is a, but would be yes. It would be yes if it was, if we used just the subset symbol. That's the key. Could be equal to if we wanted it to be. And then finally, what's the cardinality of A? How many elements are in the set A? Dun dun dun. The answer is 3. Yes, the number of elements in A is 3. Hopefully that wasn't too bad. And hopefully all these definitions are now making sense, now that you've given them a shot yourself. Okay, more stuff. Take a second to think about these. Is R, the set of all real numbers, a superset of Q? Is it bigger, and is everything in Q contained in R? And the answer is yes, because actually that's how we define it to be. R contains all of Q, but also the irrational numbers. So totally, it's a superset. It's got more stuff, and got more stuff in Q, and Q contains all of our stuff. Some of our stuff, that is. Likewise, is Z plus a subset of N? Remember that Z plus is equal to 1, 2, 3, on and on and on towards positive infinity. It's all the positive numbers. And then n, the natural numbers, start at 0. And they go 0, 1, 2, 3, on and on and on in that direction. Excuse me. And so, yes, it is a subset because, well, there's the 1, there's the 2, there's the 3. And it all matches up, even though it's an infinite set. So don't be scared. Even if it's infinite, it still works out. Okay, so that's both true in that case. So that is a nice little example, I think. And now back to more notation. Sorry, I told you, I warned you. Can we, as computer scientists, we like to test things and mess things up, see if we can call a function with a weird input and see if it still works. Make sure that it still works. And so one of those things we can call the set function, I guess, with a set itself. So you can actually put sets inside of sets, and that's an okay thing to do, which is weird. Very weird to think about, but it's possible. So here's my example A, and that is, it holds the set inside of it, 1, 2. A itself is a set. I'm eventually going to close it off. It holds the empty set, holds nothing. It holds the set 1, 2, 3, which is a different set from 1, 2. It holds the set containing 1, and that's A. What? So I guess that's the empty set, not 0. now we can talk about weird things. So normally we have like a set, another set, and like a subset symbol. But no, now we can have an element of symbol because the set 1, 2 really is inside of A. Weird, huh? The empty set, it's sitting there inside of A. But the number 1 itself, the element 1, is not inside of A. It's inside of one of the inner sets of A, but it's not inside of A itself. That would look something like this, and that's not there. This is like the element 1. The element 1, that's an E, and this is the set containing 1, which are different things. They're not the same. That's because 1 is not equal to the set containing 1. And I'll get really good at drawing braces this semester. Not there yet, though. Okay? So once you have that, you can go even further and talk about all the possible subsets of a set. And that's called the power set. Okay? Written in 2 different ways, depending on the book. So that's a set of all subsets of a set A. And it's written like this, P of A. But your book doesn't like to use italics, and so it looks like a predicate symbol, unfortunately. So for example, if this was your set A, it was 1, 2, 3, the set we know and love, then the power set of A is the set of all possible subsets of A. So if I put A over here, here's A, 1, 2, and 3. Well, the empty set's a subset of any set, yes. So you can just pick out nothing from a set. That's totally fine. The set containing 1, that's a subset of A. 2, subset of A. Just containing 3, that's a subset of A. The set 1, 2, yes, that's a subset of A, because you can just pick it out like that. Similarly for 1, 3, and 2, 3. And then the whole thing, of course, is a subset, because every set is a subset of itself. So you have 8 different, 3, 4, 5, 6, 7, 8, 8 different subsets of the set A, and that's actually a pattern, because if you have a set that contains n elements, the power set must contain 2 to the n elements. And this will make a whole lot more sense once we talk about counting later in this class. But my hand-wavy proof for you right now is, okay, if you're trying to determine, like you're trying to pick out a subset of A, and you're trying to think of which one to choose, you can consider every possible element. And for each element, you have 2 options, to either include it in the subset that you're trying to make, or to not include it. And because you have 2 options, and you have n elements, you can just multiply 2 by itself n times. And that is why every power set has 2 to the n elements, when that original set had size n. So this might be really, really confusing, putting sets in sets, especially with empty sets involved. And so I found a fun little tweet that I want to show you about. You can imagine that a set is just a Tupperware thing, and it contains elements if it wants to. But if it doesn't, that's the empty set. Okay, it's just a set without anything in it. And that's quite different to, it's not equal to, the set containing the empty set. So here's a set, and it holds itself, the empty set, inside of it. You see that? So it holds itself a smaller empty Tupperware. So hopefully that helps you understand the difference between the empty set and the empty set being inside of another set. Yeah? There's a huge, huge difference. They're not huge, huge difference. They are not the same. Okay? So that is that. And now let us talk about another example. So here's a set containing sets, and I want you to think about them. Okay? Think about all this stuff. So X is this whole big thing. Oops. I was trying to highlight, but I accidentally moved. Okay. So think about this for a second. All this stuff. What do you think? So here's X up here. 1, 2, 3, the set 2, 3. 4, the set 5, 6, 7. That's X. That's the whole thing. So what is the cardinality of X? So remember, that question is, how many elements does X itself have? Don't go counting the elements of the inner sets. No, that's just one element to X from X's perspective. So there are 1, 2, 3, 4 things inside of X, and I hope you got that. 4 elements. Is 2 an element of X? Well, it's there, but it's in an inner set. It's an element of the set 2, 3, but not an element of this set, because 2's not sitting outside of anything. So the answer is no. I hope you see that. is the set 2, 3 a subset of X? Why, this is a very, very tough question. So let's discover this. Is 2, go back to the definition, is 2 an element of X? Is 3 an element of X? And actually neither of them are. The answer is no. 2, 3 is in X, but it's 2 itself is not an X, 3 itself is not an X, and that's what it means to have a subset. Because remember what subset means. This would imply that 2 is an X and 3 is an X. That is actually not true. The whole set 2, 3 is an X, but 2 itself is not there. That would be like out here. 3 itself is not there. It would be like out there. Okay, so that's really weird to think about, but that is how you do it. Okay? It would be true if you wrapped around more braces, because then this is one element and it's there. So that's really, really hard to think about, and I understand. That's why I'm giving you this example. So this was kind of a trick question, I guess. The set containing the set 2, 3 is in fact a subset of X. Though. Okay, so that was a hard little question. How about this one? Is 5, 6, 7 an element of X? Yes, it is. It's one thing, it's sitting right there. Okay, so that was the hard one right there. Hopefully you got it. If you did, hopefully you understand it. If you got it, I am very proud of you. Okay, so let's come up with the power set of 8, 9, and 10 of that set. So that's the set of all possible subsets of 8, 9, and 10. So are you ready? Dun, dun, dun. You can always choose nothing, the empty set, and then you can always choose one element. The set 8, the set 9, the set 10. Totally fine. Now you can start choosing two elements. You can pick the two. 8 and 9. 9 and 8 is the same set, so we're not going to continue and write that one. Then you can have 8 and 10. Then you can have 9 and 10. And then you can have all three. 8, 9, and 10. We can check ourselves to make sure that this all has, this set has 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. Yes. Cool. So we did it right. So that is the power set of the set 8, 9, and 10. It's the set of all subsets of that set. And you can do power set multiple times, which is fun. Very fun to think about. So let us work on this from the inside out. Let's first do the power set of the empty set, and then we'll do the power set of the power set of the empty set. So the power set of the empty set is all the stuff that, all the possible subsets of the empty set. And so it's the set of all subsets of the empty set, but there are no subsets other than nothing. Okay? So I hope you see that this is the power set of the empty set, and we can check ourselves, we can confirm this, because the power set of any set is, the size of it is, maybe I'll put it down here. The power set of the empty set, the cardinality of that is 2 to the size of the empty set, which is 0. 2 to the 0 equals 1. So there better be one thing in this set, and there's only one possible subset of nothing, which is nothing itself. Okay, hopefully that makes sense, because nothing is always a subset, and we had nothing else to take. Okay, so hopefully that makes sense. Sorry, that is a weird concept, but now you know it at least. You can just memorize it if nothing else. And so now we can take the power set of that. The power set of the empty set is, well, it's all the different subsets that you can make out of this. And remember that it's the size, the cardinality of this must be power set of the empty set. It better be the cardinality 2 times the cardinality of this guy, which is 1, which equals 2. So there better be 2 things in this. And so let's find those 2 things. So there's always the empty set that's a subset of everything, of anything. And then there's also, for this one, all the subsets of this, there's also the set itself. Bam. I can draw that better. Bam. Do you see how these are different? Remember, these are different. Those are the subsets of this set, which is the power set of the empty set. So the power set of the power set of the empty set is the set containing the empty set and also the set containing the empty set, which is really, really hard to say in words. So that's why we include all these symbols everywhere. And so hopefully that is all making some sense. Okay, and I think this is where I want to stop today. So we're going to come back and talk about these fun concepts called union and intersection that really help us understand like what sets are good for, because then we can talk about how to compare things in a better way, and then we'll move from there. But that was your first taste of sets, and hopefully it wasn't too bad. There is a ton of notation, but once you learn it once, the rest of everything you learn will make sense because it's all going to be defined in terms of sets anyway. Okay, so I'll see you in the next lecture.